Welcome again. This is Sarfarhan, guys. I'm solving paper 2 of AS level chemistry, May June 2024, variance 23. The duration of this paper is 1 hour 15 minutes. We need to attempt all the questions, and the total mark for this paper is 60. In order to make diagram or graph, we need to use HB pencil for that. By the way, you can use calculator. Periodic table is given at the end of this paper, and also you have uh, different important values and constants in this question paper. Okay, let me start the paper now. In question number 1, explain the lack of reactivity of nitrogen gas. On the basis of my lecture, first point which I must say you need to write it in the paper is that nitrogen molecule contain double bond. Oh, my bad. It's not double bond. It contains triple bond. A slim mistake I did. Triple bond. So it has high bond energy value. Also, hydrogen molecule is non-polar. Because electron negativity difference is 0. Covalent bonds can be sigma or pi bond. Sigma bond is always formed through head-on overlapping of orbital, which is also called head-to-head overlapping. Pi bond is always formed through sidewise overlapping of p orbital. Sidewise overlapping is also called lateral overlapping. Complete table 1.1 to show the number of sigma bond and pi bond in a molecule of nitrogen, and to describe how the orbitals overlap to form sigma and pi bond. Let me draw the structure for nitrogen molecule. This is nitrogen molecule according to my lecture. If you have triple bond, in that triple bond you have one sigma bond and two pi bond. One sigma bond and two pi bond. Sigma bond is formed through head-to-head overlapping, which is also called head-on overlapping of orbital, whereas pi bond is formed through sidewise overlapping or lateral overlapping of p orbital. A sample of aluminum reacts with an excess of chlorine. Okay, if that's the case, we need to make the equation first. Aluminum is reacting with chlorine, converting into AlCl3. Let me put 3 here, 2 here, and 2 here. That's the equation. Now state the oxidation number of aluminum in the product of this reaction. So that's the product. And we need to find out the oxidation state of aluminum in this. So it's very easy. Let's suppose aluminum is X. The charge on the chlorine atom is -1. We have 3 chlorine atom into 3. Since AlCl3 is neutral and has no charge, which is y equals to 0, the next is going to be +3. So the oxidation state of aluminum in this molecule is going to be +3. State what determines the maximum oxidation number of the period 3 element in their oxides. Well, the oxidation number refers to the number of valence electrons. All right. So in oxides, Maximum oxidation number refers to the number of valence electron. Okay. Part C. Separate sample of aluminum oxide and phosphorus 5 oxide, which is P4O10, reacts with an excess of NaOH at room temperature and pressure. By the way, aluminum oxide is basically an acidic, an amphoteric oxide, whereas phosphorus 5 oxide is basically an acidic oxide. And we know amphoteric oxide can react with both acid and alkali, whereas acidic oxide can react with an alkali, right? So give the state of aluminum oxide and P4O10 at room temperature, both are solid at RTP, all right? We have done that in the class. Write an equation for the reaction of each oxide with an excess of NaOH at room temperature. So when aluminum oxide is reacting with sodium hydroxide in the presence of water, I'll get a salt which is NaAlOH taken 4. And this salt is called sodium aluminate. P4O10, when reacting with NaOH, obviously it converting into sodium phosphate and water. Since we have 4 phosphorus here, so I need to put 4 here. We have 12 sodium atoms here, so we need to put 12 here. We need 12 hydrogen atoms here, so I need to put 6 here in order to balance the equation. Let me check oxygen. We have 12 oxygen and 22 oxygen. 4 times 4, 16 oxygen. 16 plus 6, 22 oxygen, right? So oxygen is balanced. The entire equation is balanced, in fact. Next part. The oxide of silicon reacts with calcium oxide. The oxide of silicon is basically silicon dioxide, which is also called sand or silica or silicon 4 oxide. And by the way, silicon dioxide is basically an acidic oxide because it is a non-metal oxide. All right. So when it is reacting with calcium oxide, in addition, reaction to produce calcium silicate, which is CaSiO3, the oxidation number of calcium silicate is +2. Okay, the oxidation state of calcium in calcium silicate is +2. Reduce the oxidation number of silicon in calcium silicate. That's easy. Let's suppose silicon is X. Calcium has a charge of +2. Oxygen has a charge of -2. We have 3 oxygen atom in the formula into 3. Since the molecule is neutral and has no charge, which is Y equals to 0, then X +2 minus 6 equals to 0. Then X equals to +4. So I believe silicon has an oxidation state of +4. Okay. Calcium oxide can mate from calcium carbonate in a single step reaction. Identify the type of reaction that occurs. Okay, that's an easy thing. Calcium carbonate is a group 2 metal carbonate. Group 2 metal carbonate, when decomposed on heating, they will turn to calcium oxide and carbon dioxide. So in order to produce calcium oxide, we need to decompose calcium carbonate. And if we need to decompose calcium carbonate, the type of reaction is going to be thermal decomposition. Because heating is required for the decomposition of this compound, okay? So that's the question number 1, guys. Question number 2, my bad, okay. Nitrogen reacts with hydrogen in the Haber's process as shown in reaction 1. By the way, reaction 1, as you can see, is an exothermic reaction. And we need to consider this exothermic change also, okay? Table 2.1 shows the different conditions used to produce these equilibrium mixture A, B, and C. Describe and explain the change, if any, to the percentage yield of ammonia produced in B compared to A. So the molar ratio between reactants is same, temperature is same, pressure is same. So if under these conditions, yield is 58%, so obviously under this condition, yield will remain 58%, okay? Yield remain 58%. So technically no change. In percentage yield, of ammonia. Now the main question is, there is no catalyst in this case, whereas in reaction mixture B, there is a catalyst. So one more thing, catalyst has nothing to do with the equilibrium yield, okay? Which I need to mention here also. Catalyst has nothing to do with percentage yield. Catalyst only increases rate of reaction. Describe and explain the change, if any, to the percentage yield of ammonia produced in C compared to A. Percentage yield of ammonia compared to C as compared to A. So pressure is increased, temperature is also increased. So, okay, percentage yield of ammonia produced in C, if temperature is increasing, obviously, C. Initially, the temperature was 500 degrees Celsius. Now they have changed the temperature into 1000 degrees Celsius. So I'm increasing the temperature in equilibrium mixture C, right? And since the reaction is exothermic, and if we increase the temperature in exothermic reaction, equilibrium favors towards left-hand side. If equilibrium favors towards left-hand side, obviously the yield of ammonia decreases. So I'm writing is here, as temperature increases, in exothermic reaction, from 500 degrees Celsius to 1000 degrees Celsius, equilibrium favors towards left-hand side. Thus, percentage yield of ammonia decreases in reaction mixture C. Okay. This RXN is basically reaction, short form of reaction. Okay. Describe and explain the change in the rate of forward reaction that occurs to establish the equilibrium in C compared to A. You do not need to refer the Boltzmann distribution in your answer. Okay. So when you increase the temperature from 500 to 1000 degrees Celsius, obviously kinetic energy of the molecule increases. This increases the effective collision in a unit time, and therefore rate of reaction increases. So increasing the temperature increases the kinetic energy. So if kinetic energy increases, then particles have more collision. More collision with particles that have energy greater than activation energy. So this increases collision frequency. And increases the rate of reaction. All right. Next, write an expression for the equilibrium constant Kp for reaction 1 and state the units. So Kp is basically the partial pressure of product over partial pressure of reactant. Product has ammonia, reactant is nitrogen and hydrogen. So whatever the number of moles is given in the equation, we need to make them into power. So we need to place them into the power. So partial pressure of ammonia, it has 2 moles. Moles has to be in the power over partial pressure of nitrogen into partial pressure of hydrogen. Okay. Units. Units. Okay. The unit of pressure is atmosphere here. So I'm going to use atmosphere in order to determine the unit for this expression. So if atmosphere is the unit and if it is a square, so it's going to be atmosphere square over atmosphere into atmosphere cube because there's power 3. So it's going to be atmosphere square over, since both the units are multiplying with each other, so I'm going to add the powers now. It's going to be atmosphere 4. So if I'll cancel out these, so it's going to be 1 over atmosphere square. So final unit is going to be atmosphere inverse 2. Okay. My favorite question again. Equilibrium mixture D is made when 1 mole of nitrogen and 3 mole of hydrogen are added to a sealed container at 750 degrees Celsius and 1000 atmosphere and left to reach equilibrium. This mixture contains 1.16 moles of ammonia. Calculate the mole fraction of ammonia in D. So there are various steps in this, I must say, because examiner is looking for the mole fraction of ammonia. So in order to calculate mole fraction of ammonia, we need to calculate the total moles of each component or each gas. All right, so we need to sort this out. By the way, this is your nitrogen. This is your hydrogen gas and converting into ammonia gas. Okay, this is 1 mole. This is 3 mole initially, and this is 0 mole. All right, and at equilibrium we have this much amount. Please remember that. So in the first step, I'm going to compare nitrogen versus ammonia. Now, according to the equation, both of them has 1:2 ratio. All right. At equilibrium, ammonia has 1.16 moles. So we need to divide 1.16 by 2 so that we'll get the reacted amount of nitrogen. All right. So reacted moles of nitrogen is going to be 1.16 divided by 2. So I'll get 0.58 moles. So these are the reacted moles of nitrogen. So if nitrogen initially has 1 mole and reacted is 0.58, so how much amount of nitrogen would present at equilibrium? That's what we need to find out. So moles of nitrogen at equilibrium. So it's 1 minus 0.58. So it's going to be how much? 0.42 moles. So these are the moles of nitrogen molecule at equilibrium. Similarly, we need to find out the moles of hydrogen at equilibrium, and the ratio between them is 1:3, right? Okay. So in the third step, I'm going to compare nitrogen and hydrogen, and the ratio between them is 1:3. If 0.58 moles was reacted from nitrogen, how much amount would react from hydrogen atom? That's what we need to find out. So moles of hydrogen reacted would be 0.58 into 3 is going to be how much? 1.74 moles. If initial moles was 3 and the reacted amount is 1.74, how much amount of hydrogen would be present at equilibrium? So that's my next task. Moles of hydrogen present at equilibrium. So initial moles was 3 and the reacted amount is 1.74 moles. So amount of hydrogen at equilibrium would be 1.26 moles. Okay. So I know the moles of nitrogen at equilibrium. I know the moles of hydrogen at equilibrium. I know the moles of ammonia at equilibrium. I need to add all these 3 values. Total moles. It's basically 1.16 plus 1.26 plus 0.42. So I believe total moles is going to be 2.84. Now, the last step of this, mole fraction. What is mole fraction? Mole fraction is basically moles of the gas over total moles. That's what I have given you in the formula in states of matter. Okay, so mole fraction is basically total moles. My bad. Mole fraction is basically moles of gas over total moles. So moles of gas is 1.16. It's given in the question. Total moles is 2.84. So mole fraction is going to be how much? 1.16 divided by 2.84. So it's going to be 0.408. So the mole fraction of ammonia is 0.408 moles. And that's my answer. Okay. The mole fraction of nitrogen is 0.625 in a new equilibrium mixture E. Calculate the partial pressure of nitrogen in E when the total pressure is 1000 atmosphere. See, in states of matter, I have given you three different formulas in order to calculate the partial pressure, right? Out of three, one was partial pressure equals to mole fraction into pressure. Now see, mole fraction is given, pressure is given, so we need to multiply both the values. Mole fraction is 0.625 into pressure is 1000. So partial pressure is basically 625. So 625 atmosphere is basically the right answer. Okay. Next part of the question. When oxides of nitrogen escape into the atmosphere, they may be involved in the formation of acid rain from sulfur dioxide, formation of photochemical smog. Identify the role of NO and NO2 in the formation of H2SO4 from SO2 in the atmosphere to produce acid rain. Use relevant equations to support your answer. Oh, okay. Okay. First of all, let me write the equation. This NO2 is a gas. It is reacting with sulfur dioxide in the atmosphere, converting it into sulfur dioxide, and obviously will turn to NO gas. All right. So technically, nitrogen dioxide is acting as an oxidizing agent here. It oxidizes sulfur dioxide into sulfur dioxide and reduces itself into NO. Now, NO is found in the atmosphere. It will readily oxidize with atmospheric oxygen. Converting into nitrogen dioxide gas. Now, see, NO2 starts, I mean to say that NO2 is acting as a catalyst because it involves in the reaction and it will recover at the end of the reaction as well, which means NO2 is acting as a catalyst. NO2 is acting as a catalyst, also as an oxidizing agent. Because it recovers at the end of reaction and oxidizing agent. All right. Now, sulfur dioxide is present in the atmosphere. It will combine with water to give you sulfuric acid, and this sulfuric acid causes acid rain. All right. I hope it makes sense to you. Outline how NO and H2 may contribute in the formation of a photochemical smog. That's an easy thing. NO and NO2 combines with unburnt hydrocarbon to give, oh my bad, unburnt hydrocarbon to give photochemical smog, which is also called peroxyacetyl nitrate. Also called photochemical smog. Okay, that's the end of this question. Let's move on to the next one. Let's see what we have in question number 3. Write an equation to show the reaction for the standard enthalpy change of formation of water. Include state symbols. So when hydrogen is reacting with oxygen, converting into water. Under standard condition, it is gas. It is also gas. And under standard condition, it is liquid. Now we have 2 hydrogen here, 2 hydrogen here. We have 1 oxygen here. So to balance oxygen, I need to put half here. All right. Water is one of the product in the reaction of B2O3 and ammonia as shown in reaction 2. So guys, examiner has given us the standard enthalpy change of formation data. So I'm going to make thermochemical Haber cycle for this equation. And we need to find out the enthalpy change of reaction for reaction 2. Okay, let me write the equation first. This is B2O3, then ammonia molecule, 2Bn plus 3H2. And delta H phi R we need to find out. So if formation data is given, thermochemical Haber cycle needs to start from constituent elements. By using these substances, I know that I need boron, I need nitrogen, I need hydrogen, and I need oxygen. Under standard condition, it is solid, and all these are gases. We need to put 2 here in order to balance the equation. We have 6 hydrogen, so we need to put 3 here. We have 3 oxygen, so it must be 3 by 2. Okay, let me put the arrow upward because the formation data is given. Now, Bn has a value of minus 134. We know that it has 2 moles in the equation, so we need to multiply the energy value by 2. The formation of water is minus 286. We know that it has 3 moles in the equation, so we need to multiply by 3. B2O3 has minus 1264. Ammonia has minus 46. Since it has 2 moles, multiply by 2. Okay, so we need to make a clockwise arrow so that we can align the values very easily. This arrow and this arrow moves in a clockwise direction, which is why I'll take all these values as positive and I'll take these 2 values as negative, and I will equate all the values with 0, right? So it's going to be delta H, standard enthalpy change of reaction, plus minus 1264 plus minus 46 times 2 minus 134 times 2 minus 286 times 3 equals to 0. So delta H by R is going to be how much? I believe it's plus 230 kilojoules per mole. All right. Let's move on to the next part. Boron carbide is a hard crystalline solid that has a melting point greater than 2000 degrees Celsius. If it has a crystalline solid with hardness and has a high melting point, that means it has a giant molecular structure. To suggest the structure and bonding in boron carbide. Structure bonding is covalent and structure is joint molecular. Okay, joint molecular. 100 gram of pure boron carbide contains 78.26 gram of boron. Okay, so mass of boron is given, which is 78.26 gram. Now carbide. So we have two elements in boron carbide. One is boron and the other one is carbon. And the total mass of sample is 100. So we need to subtract 78.26 so that we'll get the mass of carbon from here. So 100 minus 78.26 is going to be 21.74. So 21.74. The AR of boron is given in the periodic table, which is 10.8. The AR of carbon is also given in periodic table, which is 12. Let me calculate the values so that I'll get the answer. So this value is going to be 7.246. And this value is going to be 1.811. Now 1.811 is the least value. So in order to calculate the simplest ratio, we need to divide the value on both the sides. So it's going to be 1.811. It's 1.811. So it's going to be 4 and it's going to be 1. So how many boron we have? 4. And how many carbon we have? Only 1. So the formula, empirical formula of boron carbide is going to be B4C or CB4. Okay, I hope it makes sense to you. That's an easy part. Next question, question number 4. Ammonia reacts with HCl to produce ammonium chloride as shown. Draw a diagram to show the ionic, covalent, and coordinate bonding present in a formula unit of ammonium chloride. So we need to make the displayed structure for this. This is the covalent bonding. This is dative bonding because dative bonding is represented by an arrow. This is positively charged ion. And since we have chloride ions, so I believe in order to show the ionic bonds, I think I need to show chloride like this. Okay, both plus and minus shows ionic bonding. So this one is covalent. This clear-cut plus minus charge shows ionic bonding, and this arrow shows dative bonding. An exothermic reaction occurs when ammonium ion is added to hydroxide ions. By the way, ammonium ions is a conjugate acid, and by the way, it is a conjugate base. So if both are reacting together, obviously the type of reaction is going to be an acid base. Acid base reaction. Construct an ionic equation for the reaction of ammonium ions and hydroxide ions. We have done that in nitrogen and sulfur, all right? So it's ammonium ions and hydroxide ions. So what we can do is, it is a conjugate acid, so it donates proton. It is a conjugate base, so it accepts proton. On the basis of that, I'll make ammonia and water as the product. Substitution reaction of ammonia and hydroxide ions with halogen alkanes both involves lone pair of electron. Name the role of ammonia and hydroxide ion in these reactions. Obviously, they will serve as a nucleophile. They will used as a nucleophile. Okay. Suggest which species ammonia or OH minus is more reactive during these reactions. Explain your answer. Obviously, ammonia is more reactive. Because nitrogen is less electronegative element than oxygen. So it donates its lone pair easily. Okay. Part D. When 2-bromo-2-methyl-propane reacts with hydroxide ion, two mechanisms, SN1 and SN2, both occur. The SN2 mechanism has a slower rate. Okay. So 2-bromo-2-methyl-propane. First, we need to make the structure. Propane means 3 carbon atom. 2-bromo means on the second carbon atom, we have bromine and methyl group both. So that's the structure of 2-bromo-2-methyl-propane. And from this structure, we conclude that it's a tertiary carbocation. Tertiary. So for all SN2 mechanisms, um, we'll get the one hump graph because reaction takes place only in one step, if you remember. So what we need to write is, this is the one step reaction, okay? Oops. Okay. This is the one step reaction for SN2. All right. Okay, this is SN2 reaction pathway. And this is SN1 reaction pathway. So complete figure 4.2 to show the mechanism of the SN1 reaction that occurs when this compound reacts with ammonia to produce this, include charges, dipos, lone pairs of electrons, and curly arrows as appropriate. Okay. So let me write the formula first. Let me write the structure first, in fact. Formula is given, so we need to write the structure first. That's, I think, 2-bromobutane. So we need to make the structure like this. Okay. So that's 2-bromobutane. By the way, carbon is less electronegative, so it has slight positive charge. Bromine is more electronegative, so it has slight negative charge. Okay. So, so first of all, we need to remove bromide ion through hydrolytic fission. And as a result, you will get a carbocation with bromide ions. And this one has positive charge with one hydrogen, which means it is secondary carbocation. Okay. This leads. Now we have ammonia molecule. Ammonia has a lone pair. It donates its lone pair to the electron deficient carbon so that a dative bond is formed between this carbon and this nitrogen, and that dative bond is represented by this. As you can see, nitrogen has 4 covalent bonds, which is why nitrogen has positive charge. And the positive charge of nitrogen makes it unstable. In order to get the stability, nitrogen needs to remove its positive charge, and for that nitrogen needs only one electron. Obviously it will take the electron from hydrogen atom, but for that I will use bromide ions here. Now these bromide ions reacts with hydrogen ions so that I'll get HBr here, and the electron of hydrogen obviously shifts on nitrogen so that nitrogen can neutralize its positive charge, and that's how the product is obtained. Okay, I hope it makes sense to you. Okay, identify the inorganic product that forms in the reaction in figure 4.2. Inorganic product in figure 4.2. Inorganic product. I think inorganic product. Inorganic product. Oh, see, solution has HBr, solution has ammonia. So this is alkali, this is acid. Both of them react together to give ammonium bromide. So ammonium bromide would be the inorganic product, which is formed due to the reaction between these two species. All right, let's see. Give the systematic name for the organic product. This, that's a systematic name, CH3. Let me write the structure of organic product first. This is NH2, this is CH2, and this is CH3. So basically it's two amino butane, okay. Or you can even write, since we have 4 carbon atoms, so it's butane. On the second carbon, we have 2 amines, so it's butane 2 amine. Both are acceptable from my perspective, okay? Complete table 4.1 by drawing the structural formula of the intermediate that is formed when 2-bromo-2-methyl propane reacts in an SN1 reaction. So from 2-bromo-butane, I'll get the secondary carbocation from 2-bromo-2-methyl propane. Let me write this structure first. This is 2-bromo-2-methyl propane. So if I use SN1 mechanism, obviously SN1 mechanism takes place in 2 steps. So in the first step, I'll make the tertiary carbocation. So I'll remove this bromine in the form of bromide ion, and therefore I'll get this structure. Okay. All right. Identify the halogenoalkane in table 4.1 that has the greater tendency to react using the SN1 mechanism. Explain your answer. Obviously, 2-bromo-2-methyl propane has a greater tendency to react via SN1 mechanism because it is forming tertiary carbocation, which is more stable than secondary carbocation of 2-bromo-butane. And why it is more stable? Because 3 alkyl groups are attached to carbon atom. That means these 3 methyl groups has a positive inductive effect. So because of positive inductive effect, this charge is going to be neutralized more as compared to this charge. Okay. So 2-bromo bromo 2-methyl propane has a greater tendency to react via SN1 mechanism. Because of the stable 3-degree carbocation which is stabilized due to the positive inductive effect of electron donating alkyl group. Next, question number 5. M reacts to form R by the addition of one reagent as shown in figure 5.1. Identify the reagent and conditions for this reaction. See, M is basically a cycloalkene, all right? Technically, it is an alkene. So if it is an alkene and it gives you diol, that means reagent must be cold dilute potassium magnate 7. Potassium magnate 7. R is also made from M by 2 steps as shown in figure 5.2. Identify the reagents and conditions for step 1 and 2 in figure 5.2. Step 1 and step 2. Step 1. So I'm adding bromine on the adjacent carbon atom, which means this must be aqueous bromine, and bromine are replaced to OH. So reagents and conditions for step 1. So reagent is going to be aqueous bromine, and condition is room temperature and pressure. Obviously in dark. Step 2. So in place of Br, I'm writing OH. That means the substitution reaction because it is a halogen alkane. And for substitution reaction, I can use aqueous NaOH. And obviously, I will heat the reaction mixture also. Okay. Name the mechanism for step 1 in figure 5.2. Step 1 is electrophilic addition reaction because all alkenes undergoes electrophilic addition reaction. Oh, part C. The infrared spectrum of R is shown in figure 5.3. Okay. Use the absorption region above 1500 centimeter inverse when answering this question. Add F to figure 5.3 to identify the peak that is present in an infrared spectrum of both Q and R. Identify the bond that corresponds to absorption for F. So both Q and R have the same peak. Both Q and R. Where is Q and R? Okay, this Q and this R. Both of them have same cyclic ring structure, and this cyclic ring structure has CH group or CH bond. So that's the only thing common between these two compounds. So this peak is going to be F because this peak represents CH, and CH exists in both Q and R. So CH is 2850 to 2950 centimeter inverse. Okay. Okay, next is add G in figure 5.3 to identify the peak that is not present in the infrared spectrum of Q. Infrared spectrum of Q that is not present. Since it has OH, so OH, the peak of OH appears at around 3600 centimeter inverse. There is no OH here, which means Q doesn't have a peak which appears at 3600 centimeter inverse. Okay, so there is no OH group in Q, which means the peak of OH never appear in Q, and that is basically what? G. So it must be G, and that represents OH group. Okay, so OH group is hydroxy. Hydroxy appears under this range of infrared energy. So this OH, which appears at 32 to 3650 centimeter inverse. All right. Next. But that's a lengthy question, guys. Y is made from Q in a 3-step reaction. Okay. So this is halogen-alkane reacting with potassium cyanide in ethanol. So this must be the step of reaction. And in this step of reaction, carbon atom is increased. So what we can do is we need to replace bromine, and we need to attach cyanide in place of bromine. So what we can write here is that we need to attach cyanide here, and we need to attach cyanide here. Okay. Now what's next is this CN is converted into CWH, which means in step 2, I'm going to use acid in the presence of water as a reagent. Condition is reflux, and the type of reaction is acid hydrolysis. Okay. Now the next part of the question is that carboxylic acid under reducing agent will turn to primary alcohol. But that's easy, and that reducing agent must be lithium aluminum hydride, must be a stronger reducing agent, because it must be more than 1-step reduction. All right. So draw the structure of W in the box in figure 5.4. I did that. In step 2, W is heated with HCl to produce X and an inorganic product. Identify the formula of the inorganic product. Okay. Whenever CN is converted into CWH, obviously you will receive ammonia gas also. Since reaction takes place in the presence of HCl, so this ammonia and HCl combine together to give ammonium chloride. And there's a tricky part again, because this hydrochloric acid and this ammonia are reacting together, converting into ammonium chloride. In step 3, X reacts with reducing agent Z to produce Y. Complete the equation for the reaction of X and X with Z. Use a molecular formula to represent organic product. Use delta H to represent one atom of hydrogen from Z. Okay. Identify Z. Z is basically lithium aluminum hydride. And let me count the carbon atoms here. 1, 2, 3, 4, 5, 6, 7, 8 carbon atom. Let's count hydrogen. 2, 4, 6, 8, 9, 10, 11, 12. 12 hydrogen atom. And 2 oxygen atom. And obviously 2 water molecule left. Okay. So that's the balanced chemical equation. We have 14 hydrogen atoms here. We have 14 hydrogen atoms here. We have 3 oxygen here. We have, ouch, how come? Okay, no issue at all. Since we have 4 oxygen here, we have 12 and 2 oxygen here, it means 2 oxygen left. So which means 2 water molecules are formed. So we need to put 4 here. Okay, now it's balanced. 12 plus 4, 12. So 12 plus 4, 16. 12 plus 4, 16. Oxygen has 3. Ouch. Oh, sorry. 2 and 2. 4 oxygen atom. My bad. 2 plus 2. 4 oxygen atom. 12 plus 4. 16 hydrogen atom. 8 carbon atom. That's balanced chemical equation. Okay. My goodness. Oh, that's the end of this paper, guys. Thank you very much.